Ionic bonds involve the transfer of electrons from a metal to a nonmetal. You can easily tell an ionic bond is formed by identifying the first element in the substance. For example, sodium chloride, or NaCl. I can tell this is an ionic compound because the first element in the substance, sodium, or Na, is a metal. How about something like carbon dioxide? Well, the first element in the substance is carbon. Carbon is a nonmetal. Oxygen is also a nonmetal. The attractive force that involves the sharing of valence electrons between two nonmetals is known as a covalent bond. There are two types of covalent bonds. Let's define them now and talk about them in more detail in a minute. A nonpolar covalent bond occurs when the two nonmetals share valence electrons equally. A polar covalent bond forms when the valence electrons are not equally shared between the two nonmetals. Two or more nonmetals will work together to achieve a full valence shell by sharing electrons to form a covalent bond. Covalently bonded substances are always classified as molecules because two or more atoms combine. Many covalently bonded substances, like CO2 and H2O, also fit the definition of compounds, atoms of two or more different elements combining via chemical bonds. Now, why are two nonmetals forming a different type of bond? It has to do with the size of the nonmetal atoms and the fact that removing an electron from a nonmetal requires a lot of energy. Since nonmetals have such high ionization energies, neither atom is willing to lose electrons. Instead, the valence electron clouds of the nonmetal atoms overlap, and the valence electrons are free to move between both atoms that form the bond. The nonmetals are sharing the electrons in their valence shells. Okay, how can we represent this with an electron dot structure? Let's look at chlorine gas, which has the formula Cl2. Chlorine is a halogen in group 7 on the periodic table, so each chlorine atom needs 7 dots. Now, I'm going to use X's for my dots on one chlorine atom, so we can tell the different atoms of chlorine apart. Each chlorine atom is so close to having a complete valence shell. If they could share this one lone electron, they would both achieve a full valence shell. So that is exactly what the nonmetal atoms do. The pair of electrons I have indicated here counts as a pair for both chlorine atoms. So this chlorine atom has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And this chlorine atom has 2, 4, 6, 8 valence electrons. By forming a covalent bond, both atoms have achieved a full valence shell. How about water, or H2O? Oxygen is in group 6, so we need 6 dots to represent the 6 valence electrons. The correct electron dot structure will have 2 pairs of electrons and 2 unpaired electrons. An oxygen atom would love to get 2 more electrons to achieve a noble gas electron configuration. Each hydrogen has 1 valence electron, but they would like to have 2. Remember, hydrogen and helium follow the duet rule. Do you see how these 3 atoms are going to interact to form a water molecule? If each hydrogen shares its 1 valence electron with one of the unpaired electrons from oxygen, then all 3 atoms end up with a full valence shell. Oxygen following the octet rule, 2, 4, 6, 8 electrons, and each hydrogen following the duet rule with just a pair of electrons. So, what are the properties of covalent compounds? In general, covalent compounds have lower melting points than ionic compounds. For example, the ionic compound table salt, or sodium chloride, or NaCl, melts at about 800 degrees Celsius, while the covalent molecule table sugar, or C12H22O11, melts at about 190 degrees Celsius. Ionic compounds are good conductors if melted or dissolved. Covalent compounds are poor conductors no matter what state they are in. Ionic compounds exist as solids. whereas covalent compounds can be found in nature in all three states: solid, liquid, or gas. Similar to ionic compounds, covalent solids are also brittle in general. Think of the ice here. Many ionic compounds are soluble in water, but covalent compounds are only water soluble if they are polar. What the heck is polar? Wait for it. We're getting there. Just one quick detour. Stay with me. There's a reason for this detour. Our physics friend, Roy G. Biv, helps us remember the colors of visible light in order of increasing frequency or energy. Well, we also have a chemistry friend. His name is Hofbrinkel. He helps us remember the 7 nonmetals that exist in their natural form as diatomic molecules. On Earth, you will never find a lone atom of hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine. These elements react vigorously to complete their valence shell, and many times this simply means reacting with another element of their kind. The 7 diatomic molecules are H2, O2, F2, Br2, I2, N2, and Cl2. What's interesting to me is the fact that these elements kind of form a 7 on the periodic table. Hydrogen ruins it a little bit. I'm going to use our friend Hofbrinkel to explain the types of covalent bonds that can form. A single covalent bond forms when nonmetals share one pair of electrons. This occurs in diatomic hydrogen. One shared pair of electrons is often represented by a single dashed line between the nonmetals. A single covalent bond also occurs in the diatomic molecules of fluorine, bromine, iodine, and chlorine. A double covalent bond forms when 2 pairs of electrons are shared between nonmetals. A double covalent bond forms between the oxygen atoms in O2. 2 shared pairs of electrons are represented as 2 dashed lines between the nonmetals. A triple covalent bond forms when 3 pairs of electrons are shared between nonmetals. 2 nitrogen atoms combine covalently by forming a triple bond. A triple bond can be represented between nonmetal atoms by 3 dashes. All right, now there is another way to classify a covalent bond as well. A covalent bond can be either polar or nonpolar. This classification deals with the sharing of electrons. Very rarely are the electrons that are shared by 2 nonmetals forming a covalent bond shared equally. Usually one atom is what I like to call an electron bully. What really happens is one nonmetal atom is able to attract the valence electrons more than the other. This causes the shared electrons to spend more time in one atom's electron cloud than the other. The sharing is unequal. Unequal sharing of electrons results in the formation of a polar covalent bond. Identifying a polar covalent bond is pretty simple. A polar covalent bond forms anytime 2 different nonmetals share electrons. Water, or H2O, is an excellent example of a molecule with polar covalent bonds. The oxygen nucleus, with its 8 protons, forms a stronger attraction to the valence electrons in the bond when compared to hydrogen and its puny 1-proton nucleus. This means that the shared electrons actually spend more time around the oxygen atom, making the atom partially negative. This symbol here is a lowercase delta from the Greek alphabet. In chemistry, this symbol means partially. So delta negative means partially negative. Well, if the oxygen atom is hogging the valence electrons, then the hydrogen atoms do not have as many electrons in their valence shell. Therefore, the hydrogen atoms are partially positive. See the delta positive. So similar to the north and south poles of the Earth, or the north and south poles of a magnet, or the positive and negative poles of a battery, the water molecule ends up having a partially positive pole around the hydrogens and a partially negative pole around the oxygen. The unequal sharing of electrons creates what's called a dipole. The only way for electrons to be shared equally in a covalent bond is if a bond forms between 2 of the same nonmetals. A nonpolar covalent bond is due to equal sharing of electrons, and with equal sharing, no dipole forms. All right, time for that detour to make sense. The best examples of molecules that form nonpolar covalent bonds are your chemistry friend, Hofbrinkel. The diatomic molecules involve two of the same atoms bonded together to form a nonpolar covalent bond. All right, let's finish up with a comparison of the properties of polar and nonpolar covalent bonds. The big difference is in polar covalent bonds, electrons are shared unequally. In nonpolar covalent bonds, valence electrons are shared equally. Polar covalent bonds formed between two different nonmetals, whereas nonpolar covalent bonds formed between two of the same nonmetals. Lastly, a polar covalent bond results in the formation of a dipole, a region of partial positive and partial negative charge in a molecule. No dipole exists in a molecule with nonpolar covalent bonds. That will do it for this video. So until next time.